Tuning is the process by which we find this magic value of k that gives us the right balance between overfitting and generalization. So now we have two kinds of unknowns. We have the parameters, the probabilities that we need to learn from the data. We learn the probabilities of the features given the label and the probabilities of the labels. And then we have to figure out the amount of smoothing to apply so that our model generalizes well on unseen data. So we have to find that magic value for the hyperparameter. K here is our hyperparameter, and we have to keep trying different values of K, vary it up and down until we get the perfect balance between overfitting and generalization. So we do that on the validation data. We vary the values of K and we note the accuracy of the validation data. And then we pick the value of K that gives us the best accuracy on the validation data. So the parameters, the probabilities we learn from the training data. If we were to measure the accuracy of the training data, we get the best accuracy when K is equal to 0, when we have no smoothing at all, right? So that's our accuracy on the training data. It falls as K increases. We tune K on the validation data. So we don't use the training data for K. We use the validation data for K. And what happens here is that the accuracy rises with K. The accuracy on the validation data rises with K. And then with too much smoothing, it falls down again. So we test on the validation data for several values of K. And we pick the value of K that gives us the best accuracy on the validation data. So here, that would be somewhere around here. This is where our accuracy on the validation data peaks. So we pick the corresponding value of K. We say this is the amount of smoothing that gives us the right balance. That gives us the best results on the validation data. Note that it doesn't give us the best results on the training data, and that's fine. Our goal is to get good results, good accuracy on data we have not seen. It's not to get good accuracy on the training data. We get evaluated not on the validation data, we get evaluated on the test data. And the test data may not follow the validation data exactly, but that's okay. This is the value of K that we'll go with. We cannot pick K based on the test data. That is cheating, and that won't give us good results on unseen data. So we pick this value of K here based on the validation data, and then our accuracy is the accuracy corresponding to the test data. So our final test has to be done on the test data, and that's what gives us the accuracy of our system. Before we even start working on a classifier, we need to get a baseline. We need to know how hard the task is, and we need to know what we're aiming for. So we need to be able to define what a good accuracy is. The most frequent label classifier is sometimes used as a baseline. That's a weak baseline. It gives all test instances the most common label in the training set. So let's say for the spam filter, I label everything as ham. Since 2/3 of the emails are ham, I'm going to get 66% accuracy. And I haven't done any classification. I haven't done any work. Just labeling everything as ham gives me that accuracy because 66% of the messages are ham. So that's not a good accuracy. So a spam classifier that has a 70% accuracy is not very good. For a better baseline, we should use previous work done in the domain or done on the subject. That will be a better, strong baseline. In summary, the naive Bayes assumption takes all the features to be independent given the class label. We can build classifiers out of a naive Bayes model using training data. Smoothing is important in real systems, and naive Bayes models tend to perform well when the features are homogeneous.